Welcome back. This is an Aleks training video on identifying the important intermolecular forces in pure compounds. So every molecule reacts many times with other molecules around it. Only very few don't react at all. And the chemistry is not always apparent. Sometimes the chemistry is not breaking bonds and making new bonds, but just a small tug of attraction between one molecule and the neighboring molecule in the same jar. And so intermolecular forces are very important when you want to describe material. You want to say what its boiling point is, or whether it's a liquid at room temperature or whatever, a gas. So the three main types that we're going to look at today are dispersion forces. And dispersion forces are also called London forces. So many times I'll call them London forces, but they're called dispersion forces. The second type is called dipole forces, and dipole has to do with polar molecules. Okay, so polar molecules, remember, have one side that's positive, so pole referring to polar. One side positive and one side negative. Remember, we called it delta positive and delta negative. Okay, and then hydrogen bonding, which are the three types. Remember, are some kind of an electronegative with hydrogen. So an oxygen, nitrogen, fluorine reacting with another molecule like that. So in this example, they're asking us to look at four compounds and tell what intermolecular forces apply. Well, the easy one is that all of them have London forces. Every one of them have dispersion forces. Every molecule has some slight attraction to another molecule. And I'll explain that better later, but really what's happening is if you have, let's say you have an electron around some kind of a nucleus, and they're all flying around randomly. At any split second, you may have more electrons on one side than the other. Okay, as they're all whirring around, you may have a moment where you have more electrons on one side than the other, and that makes that it has a slight negative side to it, and then the other side would be a slight positive side. So if you can imagine billions of molecules sitting all close together, all of them zipping around so fast, and then momentarily one side be negative and the other side be positive, sometimes these neighboring molecules are going to attract each other. So that's London forces. Okay, all right, so let's look at these four molecules. Okay, the easiest one, we'll do the easiest one first, is, I forgot to say, they're all dispersion. So you can mark dispersion on all of them because all molecules have dispersion or London forces. Now, what's a dipole? Dipole is where the electrons are pulled on one side of a molecule more than the other because one atom on one side is more electronegative than the other. Okay? That means we're going to have to look at these compounds and say, do they have polar bonds? If they have polar bonds, do they cancel each other out or not? Okay, so let's look at I2 first because that's easy. You're going to have I and I. They pull equally. You're not going to have one side or the other. Okay, so there's no dipole there. And there's no hydrogen bonding because I don't have hydrogen or oxygen, nitrogen, or fluorine. So iodine only has dispersion forces. Okay. Any others that are easy? Now let's do them in order. Carbonyl sulfide is a carbon in the middle with a double bond going to an S and a double bond going to an O. Okay, so if you look at the electronegativity, see there's a tug of war going on here. Which one is winning? You have to know what the electronegativity is. So I looked this up. Carbon is 2.5, sulfur is 2.5, and oxygen is 3.5, which means oxygen is winning. And so you're going to have something like that, which means this side of the molecule is delta negative, and this other part of the molecule would be delta positive. That means that that is a dipole. Okay, so we're going to have a dipole there. What about hydrogen bonding? It's got an electronegative oxygen, but it doesn't have a hydrogen. So it can't have hydrogen bonding without hydrogen. So there's no hydrogen bonding there. So let's look at the third one, ammonia. Ammonia is NH3. Let me do a Lewis structure real quick. It's got 5 in its outer shell, nitrogen, 1, 2, 3, 4, 5. And then ammonia gives you hydrogens, all right? So I already see that it's going to be hydrogen bonding because I've got nitrogen and hydrogen. Okay, so this is easy. Nitrogen and hydrogen, and the nitrogen has a lone pair. So it actually works beautifully for hydrogen bonding. Ammonia is wonderful for that. So is it polar? Okay, the electronegativity of nitrogen is more than that of hydrogen. Okay, so you're going to get the arrows in this direction, and this direction, and they don't cancel each other out. That means that this whole side is going to be more negative, and the other side is going to be positive. So ammonia is polar. Okay, so we have a polar, and what about silicon tetrafluoride? Well, silicon is right under carbon, so it's just like carbon with 4 fluorines around it. It's just silicon with fluorine, fluorine. Okay, silicon and fluorine is very electronegative, so you're going to have something like this, but all of them are canceled out. It's just like pulling a knot in 4 directions. This is 3-dimensionally 4 directions, but still all of them are pulling with the same force. So even though you have a polar molecule here of a sulfur-fluorine bond is polar, the whole molecule is not polar. So it's not a dipole. And there's a fluorine here. That's electronegative, but there's no hydrogen. And there's no lone pair at all. Okay, so it can't be hydrogen bonding. So this is how you do it. You just go one at a time, asking yourself question. You'll get it.